Hello, good morning, everybody. So I would like to welcome you to the second part of the computer vision lecture. I hope that works as well with YouTube and you could all connect. Okay, so first I would like to introduce myself. My name is Thomas Koller. I am from Hochschule Luzern. A long time ago I have studied computer science at the ETH. Also worked in computer graphics there at the Project Center for Supercomputing, which is actually what is SUPSI now, more or less. Then I stayed for a PhD in three-dimensional computer vision and some visualization. After my PhD, I was working for a while in a smaller startup company, BitPlane agency, where we did also computer vision for a three-dimensional microscopy and also some visualization. Then after some time in the startup, I went to a bigger company, Zurich Engineering. Unfortunately, a bit less of computer vision than there. And I did a couple of projects there in different roles, like as consultant or project leader or architect. About 10 years ago, I joined full-time at Hochschule Luzern, and there I do mainly computer vision, machine learning, deep learning, and also computer graphics. So I made a small plan for what we're going to do today. So we will have two presentations. First, a shorter one, which is the introduction to the new topic, semantic segmentation. And then as the first part of that topic, we look at different segmentation algorithms. There will be short breaks between the two presentations. And then after the second presentation, the rest of the time is then for exercises. So I would like to have actually many exercises for those lectures. Okay, so to the first topic today will be segmentation, semantic segmentation. But I would also like to quickly outline what we're going to do for the rest of the course. We will have three main topics. First one is this semantic segmentation. Then we will have a topic of object detection and classification. So you have already learned how to classify an object in one image. So if only that object is in an image, but often there is the case that we have multiple objects in an image. We would like to find all of them, classify them, and also localize them where they are. And then the third topic will be generating image. So we use different machine learning techniques now then to generate images. Okay, but the topic today will be semantic segmentation. Also this we will do over the next 2 or 3 courses. Today introduction and some classical and unsupervised approaches to segmentation. Then next time we will look at some supervised learning approaches to semantic segmentation that involves features and different classification techniques. And then lastly, we will see how to use convolutional neural networks for semantic segmentation, and we also look a bit closer of what we need to train those deep networks. So what is known as semantic segmentation? So here we take a look at the images actually at pixel level, and what we try to find out is a class label for each pixel in the image. So depending on our application, that could be different types of classes, but since we are at pixel level, this might be some more low-level classes that we can use later for the classification of whole objects. So maybe we would not be looking for a tree at pixel level because this is difficult to find, and you need a larger a neighborhood to see if the image actually contains a tree. But we could, for example, identify wood texture in the image, or we could identify leaves in the image, and then in a subsequent step that would help us to identify the tree. So it could be, we will see some examples. So this pixel level segmentation could be something like material detection or texture detection, or also in medical applications, some detection, for example, on the skin. Now, semantic segmentation is now quite a popular term in computer vision, but it doesn't exist for that long. Before, we had something called segmentation, and even before that, more in the beginning times of computer vision, we had something called pattern recognition. So what is actually the differences between the terms? I checked quickly on Google, so how these terms have been used. So like the nowadays more a bit old-fashioned term maybe is pattern recognition, which was popular early and then not so popular. Nowadays, image segmentation kind of stayed the same, but semantic segmentation is something that just came up in the recent years. Actually, this also these convolutional neural networks that are now mainly used to do this semantic segmentation. So semantic segmentations means we said that we want to identify what pixels belong to one specific class. Sometimes, additionally, we might want to identify pixels as belong to the same class, but also to one object, as compared to just different objects to the class, which would be like class segmentation on the pixels, or instance segmentation on the pixels. We could also a bit look at this semantic segmentation as supervised learning at the pixel level. Obviously, to find classes, we will need to have some training data to get the information. So here is a image actually from the ImageNet challenge. Classes for the difference between what we would call instance segmentation and class segmentation. Like in the top image here, you would like to detect the chairs. So if you're only interested in chairs, that would be the pixels that belong to the class chairs. They would all have the same label here. While if you want to know the pixels that are chairs but make up individual chairs, you would have different labels for the pixels of each chair, because you recognize here for different chairs. We will now look at some examples where we can use this semantic segmentation, and this would also introduce us to some of the data sets that we will use later in the lecture and also in the exercises. So here is an example that can actually be done interactively on the web, on this address here, where they build a system to segment any photo in some different classes of like landscapes. So for example, what is the sky, what are buildings, what are trees, what is a road, and this is almost instantaneous. The segmentation is very fast, and it's not perfect, but as you can see here, it's quite good. It can recognize the sky quite well. It can recognize the road. It expects some vehicles on the roads here, so that's a bit strange maybe. And also here it seems that it doesn't have a class for actually grass or something, so it has identified all of that as tree. Other possibilities that I already mentioned is like a texture recognition. So this can be used then maybe in a next segmentation step. So you would like to find out what kind of textures is in the image. And the problem here is a bit that the texture might look quite different under different illuminations. And there are some databases that list different textures in different illuminations. So if you do something like this, you would like to learn that these images here, which are of the same texture class but look differently, are then recognized by the system as belonging to the same texture here. There is also another data set that looks at textures a bit more from human perception in of view, which I find actually quite interesting. So it's not really the technical texture behind, but something like how would we identify such a texture, or how would we call such a texture. So for example, a texture banded is everything that kind of has to do with stripes in one way or another. Or okay, there's banded and striped, so that would be more parallel stripes, and this can be any stripes here. Or we have something like braided, that could be hair or other things in braids, etc. These texture classes, and so there is 47 of those texture classes, and it's a large data set. So we will use this data set in one of the exercises. We have also tried to use that in projects. So the idea is that you first identify the textures and the texture description, and then often from the texture description you can come back to have more detailed class information of a larger set of classes that you might want to find here. Another example here is material detection. That's a database that comes from Flickr. So this is a database of photos of different materials, so like paper or stone, with, as you can see, the difficulty that maybe paper here can look quite different, can have color or not color, and you would like to train a system that finds out just on what material is this specific object made of. So as you can see, maybe sometimes in these semantic segmentation approaches, we have to look at things a little bit differently than we maybe would look at them in object detection. So for example, you see here we have 3 different types of cars. So in an object detection scenario, you would like to identify all of them as cars, but now we're concerned about material detection, and in material detection these would be different classes. So this is probably made of some kind of metal, a real car, and then you have some toy cars that are made of plastic, and you have some other car that is made of wood here. So that would actually be then 3 different classes here. Or also here, difference between material detection and texture detection. So in texture detection you would just have this pattern here that you would like to detect, but here you have different materials. So this looks like could be plastic or leather, or even kind of metal here with color on it, or this shoe is probably made from some kind of fabric, and so you would like to identify the fabric here and the material here, and not really the textures of those black and white crosses. Medical imaging has always been a prominent example, I think, of those segmentation on pixel level for diagnosis. For example, in when I'm working on my PhD, I was looking on MR and computer tomography data, and we already tried to find out some different kind of classes in those images, like detection of blood vessels or fat or other things in those 3-dimensional images. Here is an example from actually a challenge on dental X-ray analysis. So maybe when you were at the dentist last time and he showed you these pictures here I'm always really amazed of what he sees in the picture, so that this may be caries or something. I usually don't see anything in these pictures. So there is a challenge to automate that what a dentist sees, so that he can that we can automatically identify what happens in those teeth here. So I think rather a challenging problem here. Also, in our lab, we had some InnoSwiss project in medical image analysis. So this was an example from eczema detection. So the idea was you have images of skin. In the first part, there was just from hands, and you want to identify if some region has eczema or has not eczema. So also on the pixel level, and then mark this here on the pixel. We will hear a bit more about the project later. One idea was just to help the doctors, for example, to measure like the area or so that is affected by the disease, something that it's not so easily done from a doctor that can just look at the hands. Other a very large area of research is of course autonomous vehicles, and there's also a lot of data sets here. We will see some examples more in a moment. And in autonomous vehicles, you want to detect in real time what happens in front of your camera, like where are the cars, where is the road, where are any people, for example. And so this is a bit not such a large data set with 200 train and test image sequences, and about 36 classes. And there is also a larger data set called Cityscale with very fine annotations in 5,000 images, and more coarse annotations in a larger set of images. Here is an example of the SegNet applied to scene segmentation from the road. So this was the example that we've seen a couple of slides before for the landscape segmentation, and here it's from a driving car. So on the top you see what the camera sees, and on the bottom the real-time segmentation here, which as you can see is in the real time, quite fast, maybe not correct in all the cases, but in the major of the cases it kind of detects the correct things. Problem here is a bit if there are some things that you didn't detect, like a car or maybe a bicycle, that is of course quite a problem. Okay, I will go over to the next example. So this is from a different group. This is a bit later work, and they work on this Cityscape dataset, and on high resolution images. They also detect the scene pixels in real time, and at 30 frames per second. So this is quite impressive, and here the quality I think is also a little bit better than in the example before. Maybe they also have a bit less classes here, so they just want to have a road, sidewalk, of course pedestrians. You see signs that are recognized. Some signs are really the signs for traffic, but it also detects other kind of signs. But I would say quite impressive here with the segmentation. Okay, so next today we will look a bit at segmentation here, and here maybe a bit an image that tries to describe of how computer vision kind of changed over the years of what was expected of computer vision in the early times of computer vision image processing, and what is maybe more happening now. So what we expected to have is kind of that we would have an input image, that we could probably detect things in the input image like edges, which I think you have done over the last in the first part of the course. So then maybe with the edges, maybe you have a half transformation to detect straight lines here, and this would help you to segment the image into different regions, and then would be the idea that you could then detect actually the objects in those images using the results of the segmentation. So the problem is a bit when you apply that to a real image, then okay, you can probably get the edges quite well enough with a good edge detection. But then when you try to use that or other approaches for the segmentation, you will usually end up with a lot of regions like here, and then it is a bit difficult to really build that system that goes from the segmentation to the recognition. And so what has happened instead is, as we will see then in our second topic maybe a bit more, is that you do not really explicitly go through these middle stages here, but nowadays you would train end to end to do the recognition directly on the input image, for example with convolutional neural networks, which will first extract the image features needed to do the recognition, and then on those features do the actual recognitions to get your classes. Okay. So this was already for the first part here, for the first presentation. Next topic we will look at this segmentation, and then look at some topics a bit in more detail here. I would, however, suggest we make a quick break of maybe about 10 minutes, grab some coffee, and then come back and we will look at the second part then with the introduction to the segmentation and clustering algorithms. So see you back in about 10 minutes. I will run a timer on that here then. Okay, so welcome back. Hope you had a good coffee break. So now we would like to look at different topics of segmentation. So what is there in segmentation that we can do? We will start with some classic techniques, but as this is a course on master level, we will not discuss everything. So maybe some of you have already heard some of the segmentation things in the bachelor. For example, there's two algorithms that are can commonly be used, which are split and merge and watershed algorithm, which we will not look at in this lecture. We will look at one actually not machine learning techniques. This is called graph cuts. Why it can also be combined with some clustering method, as we will see, and it is probably the best non-machine learning techniques that you can have for segmentation nowadays. So this is kind of like the standard approach that you can use in segmentation. But we will look at the graph cuts actually at the end of this lecture today. First, we look at some techniques that come from actually unsupervised machine learning techniques like k-means and mean shift that we will do next here. So at the end of this lecture, you should understand what we mean by using clustering for image segmentation, and how we can apply those clustering methods to segment actually an image. what are the differences between the two cluster algorithms that we will look at by k-means, what are the advantages, disadvantages of that, and of the mean shift algorithms, what are the advantages, disadvantages of that. And you should understand what is the principle behind those graph cut algorithm, and how, not the whole implementation, but how would one cut be actually calculated, or how is it determined, what is a good segmentation there. So what do we mean by segmentation actually again? So we don't have semantic segmentation, but just segmentation. We will not be able to assign any classes to the image because we don't have any training images with classes to begin with. So what we want to do instead is, from the image, in kind of a bottom-up approach, find regions that are probably similar and then later could belong to the same class. So it is a bit similar to an unsupervised learning approach, as you do not have any labeled data from the beginning. So in these examples, you have the tiger that you might want to segment, and then you have maybe some water in the background and some grass, and those could be the different regions that you would like to identify. And of course, if you would have that, that could help you then to later actually better identify the actual objects. But this is not always so easy, and it's also not so clear what kind of like the ground truth would be. So these are two images from a Berkeley data set where they have asked people to segment the image, and people responded here differently. So for one person, the segmentation is just the tiger, maybe here everything that is in water, and then everything that is in ground. But another person then has maybe looked a little bit more of how the image looks like. So, and see that the water is not uniformly, so this is part of a reflection here, which is lighter, and here, and so he segmented that differently. So it is kind of a difficult problem, and it's maybe not a unique solution. But the idea is to find some regions that share some common properties. So the first thing we want to look at here is k-means clustering. And so actually I would expect that some of you, maybe most of you, have already heard of k-means clustering in one of the other lectures. So if you have, maybe think quickly, so how is this implemented, k-means clustering? And what do you actually need for k-means clustering at the start? And will you get the optimal solution to k-means clustering? Anybody has some ideas on that? Okay, somebody said iteratively, so it's an iterative solution. You will probably stop the iteration at some time. When you stop, is it optimal? Okay, so it depends on the starting point. So with different points, we could have different results. Yes. And maybe the other question is, what do you actually need at the start? So if you would think of it as an image, what would be your input to k-means clustering if you want to do it in image processing or image segmentation? Okay, so one note is that first you need a k, This is correct. So for the k-means clustering, you need to know how many classes you need. It's also a bit of a drawback of the clustering. The other question was a bit of what do you want to cluster? So if you want to cluster image regions in the image, so you want to cluster something that is common to the region, so you will need some feature first that says you what is a common region. And one feature, for example, could be color. So you could just do k-means clustering on the color. That it would be like the straightforward approach. You could also use it on some texture features that we will look at in the next lesson. But for now, just imagine that you would do it on color. So for each pixel, you would have the 3 colors. So you would do the clustering in the 3-dimensional space of RGB, for example, or another color space. And then try to find out what is the similar colored in, what belongs together, which colors to form one of the clusters. So you need the k at the start. You need some features that you want to cluster from the start. How is it implemented? One of the most often applied algorithm for k-means, usually just called the k-means algorithm, is a little bit more correctly called Lloyd's algorithms. How does it work? Iteratively, as has been said. So you initialize some cluster centers, for example, randomly, and then you just do 2 steps. Mainly, you calculate which samples belong to which clusters, and then you calculate the mean values of those clusters that you have found, and those mean values become the new cluster centers. And then you iterate over those 2 steps that you then assign the samples again, and so on until the clusters do not change anymore. So as you can see, if you initialize the cluster centers randomly, so you might not get the same result every time. So one approach for that could to deal with that could then be that you apply it several times and just take the best result. We will have to find out what is a good result, and this is something that you then supposed to do in the exercise. The other question was, is it optimal? Well, if you get different results every time, then it's probably not optimal. Would you do an optimal solution? Yes, but this is much harder to calculate. So it's I think it's an NP-hard problem, and this is just usually not worth it. So you do an easier iterative algorithm here. So let's look maybe at a quick example of how this works here. So this is some demo application, not from me, for clustering. So this works on a 2-dimensional space. We can do some, identify some samples here. So let's make some that should probably end up in a cluster, but maybe also some in between to make it a bit more difficult. And then see what happens. So here we could place the cluster centers by ourselves, but let's take some random ones, and so this will just assign some random clusters. I think we were quite lucky to have some here and some around here, and then what you would do is you would now run the algorithm from that pair. And to see a bit better what happened, let's go back. So the first step was we have those random clusters, and then from those random clusters, cluster centers, we assign now the points to the cluster, and so for each point we will check which cluster center is the nearest. And so you have some here that might not make sense that they will remain here, but the nearest center is the gray cluster center here. So this will be this cluster, this cluster, this cluster, and these clusters. Now we have the new clusters, and now we initialize, we recalculate the centers to the mean values of those clusters. So each cluster center now goes to the middle here value, and then we start from new and assign the points to the new cluster centers. So we see some things changed. So this cluster here got some more of the samples here, so on. So the clusters have changed. Then again, we will calculate the new mean values, assign the cluster again, calculate new mean values, assign the cluster again, new mean values, cluster again, and so on until nothing changes anymore. And result was quite good. So at the beginning here, we had some samples here that were probably better in this cluster than in this one. So they actually came to this one. And I think here all the clusters actually look quite reasonable. So then you could do this a couple of times, and then you would just try to find out if it was a good solution, and then keep the best solution. And of course, a good solution would be that the points in the cluster really belong together. So like the distances of all points in one cluster should be not so great compared to the distances of points in that cluster to points in some other cluster. And that could be one measure that you could use to calculate then the result of the clustering here. Okay. Okay, so K-means clustering works quite good. It has some drawbacks. For example, the number of clusters must be given, as we have seen the K. Of course, you could apply them multiple times with different Ks and look at the result and try to find out what is the best. Another, maybe a bit more serious problem is the cluster shapes. And how are those shapes given? They are not given directly, but we use a distance function to calculate if some point belongs to one cluster. And so the distances implies that actually the cluster shapes would be like spherical in that n-dimensional shape. You could not have some elongated clusters, because then if there's some other center nearby, that will kind of steal your points here. So this could be a bit of a problem. For example, first one example. This is actually then from the exercise of K-means clustering. So at the top you have one image, which is actually an image of those of the car data set for self-driving cars, where you try to understand then the scene that the car sees, and you see the clustering here at the bottom. So it's not so bad. I think you have the sky, which is probably detected as one cluster. You have the road that is detected as one cluster. But of course, with the different cars with different colors, there were not enough clusters to separate all those cars into different clusters. And also like this color here kind of got clustered in the same color than from the road here. And also this region here with the grass is not very uniform in one cluster, but these points are different. What could you use to improve that? One idea could be to not only use the color of the pixels, but maybe also the position of the pixels, so that those green colors which are close to each other maybe belong together in one cluster, rather than with the not so green at a very different part of the image. It's also something that we will look at in the exercise. So maybe for a bit more complicated image here, some houses, and let's assume we would like to count how many houses there are here. We have obviously color, so we could probably use color to cluster them and detect then how many houses we have here. Problem here is a bit if we convert this image to a color space. Here we use the LUV space. Then some of the clusters look okay, like this one here, but other clusters that could be together here, they look not very spherical. at all, and so it's a question if the k-means algorithms would work well for that. So for that problem, there is a other clustering approach called mean shift clustering, and over the k-means, it has maybe two advantages. First, the k does not need to be given, so it finds clusters itself, how many they are, and the shape of those clusters in the cluster in the feature space is also not given, so it does not need to be spherical. What is the idea? So the idea is that from each point we now search for the cluster center. And where is the cluster center? Cluster center is where those features or where those points are more dense than at any other point. So for each point we would like to find the center where the features are more dense, and then all those points that converge to the same centers, they belong to one cluster. Okay, sounds a bit complicated. We will just see an example of that. First of all, so this is actually already an example of the result. So with this k-means, you will actually be able to achieve clusters that are not spherical. For example, all those yellow here is then one cluster that has been found in the image, and this is not spherical, and you have other clusters here grouped like around the yellow one here. So one of the problems is we would like to search for this local maxima of this feature density, but we have just given points in the feature space, and this feature distribution is not actually available directly. So how can we find a maximum then? The idea here is to apply something that's called a kernel density estimation to describe the distribution. It looks very complicated from the formula here, but it's actually not that bad at all. So what it means is you approximate a function by replacing like each sample point with a so-called kernel function. And as a kernel function, you could, for example, take this here. And what is this? This is a Gaussian function, a Gaussian kernel. So you have replaced your samples with a sum of Gaussian values. So the idea behind this is like that. So here you would have, like we are in 1D, so we have here features at some specific points in our feature space, and so for each point here we replace the point with a Gaussian, and then when we do that for each of those points we sum all the Gaussians together, and then we get those green curve here. And now the green curve is like an analytical curve, or at least it can be evaluated at any x values, and then we could actually find the maxima of this green curve, and the maxima here is where the underlying points were the most dense to begin with. And since you probably need some derivative, like maybe we could use a gradient ascent, we can actually, instead of using the Gaussian, use the derivative of the Gaussian, then we directly get an approximation of the gradient vector at that point here. So for the mean shift algorithms, what does this mean? The steps here then are as follows. We calculate the mean in an environment. That means we look at a specific neighborhood of a point x, and we use, for the calculation of this mean, we use this kernel approximation that we have seen before. Then we set the point to the mean that we have just calculated, and we continue iterating by replacing x with the mean until x does not change. It's kind of similar with the k-means clustering, and we do this for all positions in the image, with things respectively in the feature space of the image that we look. So here an example from that. So here that would be our feature space, maybe two-dimensional color space or something, and we would just start at one position. Then we look at some neighborhood of this position and calculate the mean value. So you could visualize that as you want the mean value of the positions of all the red dots that are inside that circle here. Since the dots are more dense in this part than in this part, the mean will be more in this direction. So this is the center of mass, or the mean of all those points here. And so now you will replace your starting position X with the mean that you have just calculated. You move there, then you have a different neighborhood of pixels now to look at, and you will continue as the same. So again, you will calculate the mean, or the center of mass, for all the points in your neighborhood. So here in this blue circle here, again the mean will be more in this direction, as the points are more dense here, and then you shift to the mean. That what gives the algorithms the name, as it is a mean shift to the mean. Once more, and at some point when you're at the densest position, when you've reached the densest position, then the mean value will not change anymore, and then your iteration is done for that starting pixel. So what we have actually done is we have converged from one starting position to that position here. And you could imagine that if you probably start here, you will reach the same ending position here, as this is just the densest in all the environment here. So if you do this for every point in the feature space of the image, you then define as a cluster, or some like a attraction basing all those points which converge to the same point ultimately, and those form then a cluster in your feature space. And so this would be the result what we got here from our input image in this three-dimensional space here. So this is just viewed the same image as this kernel function approximation, and what it actually does then, just like similar to a gradient ascent, that will go to the peak from your local point, gradient ascent, until you find the peaks, and these are all the peaks that appear in the images, and those give rise to the clusters. So depending if you have a larger peak or a smaller peak, this of course depends on the neighborhood of features that you look into. So the whole algorithms is you need to calculate some features, for example the colors. You could also include some spatial properties like pixel location. Then you initialize the mean shift at each of those features resulting from a pixel. You perform the mean shift until it converges, and then you merge all starting positions together that end up at the same peak, and those are then forming the cluster. Here are some results actually from the original paper on mean shift, and what you see is that it's just a flattening of the color. So you get some clusters here, like all those blue regions here are formed into one cluster. Most of the red is in one cluster, and the other colors in one cluster here. So it gets like more a posterizing effect on the image here. Some other examples for more landscape. So I think it's quite well with the grass and the roads here. Maybe a bit more difficult here with the different parts of the mountain. On the here the result on the same image that we used before for the k-means clustering with the mean shift implementation actually in OpenCV. that you can also try in the exercise. Maybe parameters were not so optimal, so it's kind of okay here and in the road, but it seems to have made a little bit too many clusters here, so it would probably have been better to change to a larger neighborhood to get the less clusters here. Yeah, so there was one question of the standard and to me for the Gaussians, if they're hyperparameters. Yes, so this depends a little bit. So I think you have maybe two hyperparameters in the algorithm. So one is, and maybe that is the more important one, that would be how large is the neighborhood here that you look at, and the Gaussian here, you could experiment with the Gaussian here. So basically you would have a Gaussian that is large enough so that it covers some of the pixels, some of the other feature points. Because if you just have a very narrow Gaussian, then you will just have a little Gaussian out of on each point. This is not what you want, because you want the global maxima here. So you have to differentiate a little bit. If you make the Gaussian larger, you will probably end up with less clusters, but more clearly defined cluster here. Okay, any more questions? Otherwise, to the min shift. Okay, so as last algorithm for today for segmentation, we would look at something called graph cuts. So what is the idea between a graph of those family actually of graph cuts algorithms? Well, the first obviously is that we calculate a graph and we cut some edges in the graph. So we have a graph that belongs that is made of nodes and edges. So you could, for example, have a node for every pixel in the image, or we will later see you could have a node for a so-called superpixel that you have clustered first. And then you have edges between those nodes and pixels. There are different possibilities here. You could have edges between every pair of pixels, but if you have a 1 million pixel image, then that will be really a lot of edges. So there will be a lot to calculate. Or you could, for example, we will use what we use in the examples here. You could just have edges between the neighboring pixels in the image. And then for each image, for each edge, you assign some weight, and you want to assign the weight so that if the weight is high, then you want to say that those image pixels are more similar. And if the weight is small, then it means those pixels are less similar to each other. And you could use different measures to calculate this similarity, for example, like the difference in color and position and so on. Okay, so a bit more formally, then we have a graph. So a graph is a set of all points, of all nodes, that would be V, and all edges, that would be E here. Then each edge has a weight that represents the similarity. And now what we want to do is we want to cut G into two graphs, which must be disjoint. So what does it mean? There can be no edge that goes from a node in one graph A to a node in the other graph B. So we remove effectively all edges between A and B here. And how do we calculate this? One idea is we assign a value to this cut, and the value of the cut is just the sum of all the weights of the edges that we have cut. Okay, so the cut of AB is the sum of all weights between U and V, where U is a node in A and V is a node in B. So here, easy example. So if you have those A and B, and you have only those edges here between, then the value of the cut between A and B would be W1 plus W2 here. Okay, so how can we use this now for segmentation? So one maybe straightforward idea would be to find out which cut has the minimal value of all the possible cuts, because a small weight means that the pixels do not belong together. So we want to find out all of the edges that we can remove which have not a high weight, and so maybe for all the possible cuts in the image, let's select the minimal cut. So let's look at the example here. So this would be an image with some pixel, and I have assigned some weights between each pair of pixels, so all the edges. So the weights are all 3 in that part of the image, and the weights are all 3 in that part of the image, and between those two parts the edges have a lower weight of 2. So what would we expect? Probably what would happen with the min cut algorithm? Of course we would expect that, right? So it's all symmetrical, and the edges in the middle have the minimum, so that must be the best cut to actually separate those two regions. But is this really the cut with the minimal value? Anybody sees some cut that that's another value? There was some question on the YouTube chat about some other chat channels. So the Discord chat is also active. So I think it might be easier then to have the Discord chat, which we can use then also later for the exercise. Yes, so somebody said a corner can be cut. Exactly, and this is the problem. So if we cut off a corner in actually those regions where we have always 3 connected, then the corner is only has a cut value of 6, while this cut has a value of 8. So this is a better cut. Well, too bad, huh? So algorithm doesn't work. Well, sorry, let's try something else. No, it's not so bad. So just min cut is not the best solution. A better solution that people came up is what they called the so-called normalized cut algorithm, and that is the graph cut algorithms that's mainly used. So the problem is, as we have seen, that the minimal cut can cut off small groups. So a better approach is this normalized cut, and this uses a different value for calculating the cut. So the normalized cut between two sets A and sets of nodes A and B in the graph, which must be disjoint, is the cut value between A and B. So remember, these are all the edges that are associated between A and B, and then V is the set of all vertices. Then associated A and V is the sum of all weights where one of the edges originates in A, where the other set can be anywhere. Okay, now let's look at what happens here, and I just noticed that I actually made a mistake here, so we can see what the mistake was. I will correct it at the end. So the idea is we will assume that this is our first A, and so what is the value of this association of B? So that would be the sum of all the edges that have at least one edge in A. Well, it's obviously all edges here, but, and I forgot that yesterday, we have to include all the edges also that start here, but go to one edge less. So the correct value is actually 38. And I put 30 here, I will correct it in a moment. So it should be 38. Then same for the other one, which is symmetrical. So, oops, will have the same values, actually also 38. And then the last value that we need is the value of the cut between A and B. Now this is easier, so this would be 8. And then if you go back to the formula, you have the cut divided by that plus the cut divided by that, and that gives you the value of the cut here. So sorry, should be 38 here. Everywhere where there is 30. And this then gives you the value of the cut between A and B. And now if you're not going to do this, but if you would calculate the same for a corner here, then this time for the corner you will not get a better value. Mainly because the association inside the corner is not so great here. So actually in that case the normal cut algorithm would find this optimal cut between A and B here. Okay, so we have a large graph, and now we have to calculate the optimal cut between all of them, which, as you can be seen, can be derived here. Okay, we will not look at this derivation. It's quite long, this paper here, but they have found a way how to calculate this optimal partition of the graph, which can be quite large, also with an iterative algorithm, and then prove that their algorithm actually works. So it's a problem we can solve, and we can calculate the cut accordingly. One of the problems maybe with the graph cut algorithms in the beginning is a bit that we have lots of pixels in an image, and if you have a lot of pixels, we have a lot of nodes in a graph. So maybe we can do some like a pre-calculation to have less nodes than in the graph. And one idea to use is so-called superpixel segmentation. So this is kind of a first step of an easy clustering, with the idea that the clustering does not need to be perfect, but as it doesn't need to be perfect, it's also much simpler to do. So you have all the cluster here, regions that you have found here, and you see that you found boundaries where there are entirely different regions here, but you have a bit over segmentation here inside, but this is then not a problem because that will be solved by the graph cut algorithms. And so this is also something we will try then in the exercise to first use this superpixel segmentation and then do the graph cuts. That one implementation of this superpixel segmentation is Slick, and if you're interested, I added the paper that describes the Slick algorithm, which is also the algorithm implemented in the library that we use. It actually comes from EPFL. So here an example of what can be done with GraphCut and the superpixels. So I haven't shown the intermediate step of the superpixels that you will be applied first on the input image, and then on those superpixels you do the GraphCut algorithms, which then effectively combines those superpixel regions. And I think the resulting segmentation as a unsupervised segmentation method is here quite good. You get here, I think, clear the grass and the road. So the sky here was maybe a bit triggered by the pole here, divided into two clusters, but the others looks quite clean, I think. Okay, so summary of what we have seen today. We can do image segmentation by clustering in feature space, for example by colors. We will look at more features in the next lecture for texture approaches. We can use k-means, but it supports spherical cluster shapes, and we need to give a k from the beginning, or we can use mean shift filtering, which supports any cluster shapes, does not need k, has some other hyperparameters of the region, and is in comparison much slower to calculate, because it needs those iteration from every starting pixel. Normalized graph cuts, usually on superpixel, I think is one of the best performing unsupervised segmentation methods. So if you ever need of anything segmentation, this might be the approach to try out first. So this would be all from the presentations. So next thing that we want to do today then would be the exercise. So maybe we'll just like quickly outline. So exercises again in Jupyter notebooks, which I think or I hope you're familiar with now. So we will look at some clustering. First, some easy clustering for some medical problem that we had in one of our projects. We want to do some green screening. That means we would like to separate the images from a green background, and let's see if we can do this by a k-means clustering with probably k equals to 2. Then an example with some more colors in it, so you would need more k's. Can you use clustering to find those figures from a game which have different colors, but also the color is not that uniform? So can k-means be used to group them all together in one cluster? And then we'd like to compare the different approaches on this image for autonomous vehicles. So first you should try the k-means on that, and then the superpixel segmentation and the graph cut, and then the mean shift, and compare the different results and maybe play around a little bit with the hyperparameters. As a further exercise, but this would be optional, is can you do a k-means with position and color? So your feature vector would include the position as well as the color. You might have to check if you have to scale any of them, and if you input that to the clustering, would that result in an algorithm that is able to cluster the different figures into different clusters then. Okay, so that would be all for the moment. I suggest I will be around on the Discord channel if there are any questions about the exercises, and otherwise then we will continue next week. So at the beginning of the week then I will also discuss the results of the exercises, and then we will continue the lectures. I think in the same setup. I will announce you the link of the YouTube channel, and I would also try to quickly edit that file and then make the streaming from today available online. So all for now. So see you on the Discord channel, and otherwise have a nice day and a nice week. Bye bye.